Google's Willow chip is touted as not just another.
For thousands of years, one question has outlasted every civilization that ever tried to answer it. Who built the universe? Not how it works, not what it's made of, but who is actually responsible for the fact that any of this exists at all? Every culture that ever looked up at a night sky asked some version of this question, and every culture came up with a different answer, and none of those answers ever fully satisfied the people who asked them. So what happens when you stop asking priests and philosophers, and instead put the question to the most powerful computer humanity has ever built? That's exactly what a team of researchers at Google decided to explore, and the results of that exploration reveal something far stranger and far more grounded in real physics than any myth humans have told themselves before. Ancient Egyptians looked at the sun and saw Ra dragging light across the sky in a boat. Greek philosophers argued about whether some unmoved mover kicked the universe into existence and then stepped back to let it run itself. Medieval theologians spent entire careers debating whether time itself had a beginning or whether the universe was simply eternal, looping backward forever with no starting point at all. Every answer was different, but the question underneath never changed. Something exists. Why does it exist? And who, if anyone, is responsible for that? Then science entered the conversation, and for a while it looked like humanity was finally getting somewhere. Isaac Newton showed that the force pulling an apple to the ground is the same force keeping the moon in orbit, which meant the universe wasn't chaos. It followed rules, and those rules could be written down as equations. Centuries later, Albert Einstein went further, showing that space and time aren't separate, fixed backdrops, but a single flexible fabric that bends around mass and stretches near speed. Gravity wasn't a force reaching across empty space. In Einstein's model, it was the shape of space itself curving under the weight of stars and planets. Then quantum mechanics arrived and made everything stranger still. At the smallest scales, particles don't behave like tiny billiard balls with fixed positions. They exist as probabilities, spread across multiple possible states, until the act of measurement forces them into one outcome. Two particles can become entangled, so that measuring one instantly tells you something about the other, no matter how far apart they are. Einstein himself was so unsettled by this that he called it spooky action at a distance, and he spent years trying to prove quantum mechanics was incomplete. He never succeeded. The universe, at its foundation, really does behave this way, even though it defies every intuition built into the human brain by millions of years of evolution on the surface of one ordinary planet. Cosmologists eventually pieced together the story of the Big Bang, tracing the expansion of the universe backward roughly 13.8 billion years to a point of unimaginable density and heat. Space itself expanded from there. Matter formed. Stars ignited. Galaxies spun into being. It's one of the most well-supported models in all of science, backed by the cosmic microwave background radiation, the observed expansion of galaxies, and the relative abundance of light elements like hydrogen and helium. But even the Big Bang model has a hard limit. It describes how the universe evolved after that initial moment. It does not, and by most physicists' own admission cannot, explain what caused that moment, or why there was anything capable of exploding into existence in the first place. Every equation eventually runs into a wall where the question changes from how to why, and physics has never been fully equipped to cross that particular line. This is where the story gets genuinely interesting, because in December of 2024, Google's quantum AI team unveiled a chip that pushed computation itself into territory that sounds like science fiction, but is very real. The chip is called Willow, and it contains 105 qubits, the quantum equivalent of the bits that power every ordinary computer. A regular bit is either a 0 or a 1. A qubit, thanks to a property called superposition, can exist as a mixture of both at once, which lets a quantum processor explore an enormous number of possibilities simultaneously rather than checking them one at a time. Add entanglement into the mix, the same spooky phenomenon that bothered Einstein, and you get a system where qubits become linked together so tightly that they behave as one interconnected whole rather than a collection of separate switches. On a specific benchmark called random circuit sampling, Willow completed a computation in under 5 minutes that Google's researchers calculated would take Frontier, one of the fastest classical supercomputers on Earth, roughly 10 septillion years, to finish. That number is a 1 followed by 25 zeros, a span of time so far beyond the current age of the universe that it becomes almost meaningless to the human mind. What made the achievement even more significant to physicists wasn't just the raw speed, though. It was that Willow demonstrated something called exponential error suppression, meaning that as researchers added more qubits to the system, the error rate actually went down instead of up, clearing a threshold for reliable quantum error correction that had been theorized since the 1990s, but never convincingly demonstrated at this scale. In plain terms, Willow wasn't just fast. It showed that quantum computers could, in principle, keep scaling towards something powerful and stable enough to tackle problems that no classical machine could ever touch, from modeling new medicines to simulating the exact behavior of subatomic particles. That last part is where the deepest questions start to creep back in, because one of the strangest theoretical explanations for why quantum computers can be so absurdly powerful comes from physicist David Deutsch, one of the founding figures of quantum computing theory. Deutsch has argued that a quantum computer's power might come from performing calculations across a vast number of parallel universes simultaneously, in line with the many worlds interpretation of quantum mechanics, where every quantum event branches reality into multiple coexisting versions, rather than collapsing into a single outcome. It's a controversial interpretation, one that plenty of physicists reject in favor of alternatives, but is taken seriously enough in academic circles that it shapes how some researchers think about what a machine like Willow is actually doing when it processes information. If Deutsch is right, then a quantum computer isn't simply calculating faster. It's tapping into a structure of reality where possibility itself is layered and branching, and where the line between one universe and many becomes far blurrier than everyday experience would suggest. So here's the thought experiment worth sitting with. If you built the most advanced quantum system on the planet, one that operates by exploring branching possibilities and behaves according to rules that already stretch the boundaries of common sense, and you asked it the oldest question in human history, what would it actually be able to tell you? Not through some mystical readout or a secret message hidden in fractal code, because that's not how these systems work. Willow doesn't produce cryptic symbols when you ask it philosophical questions, and it isn't secretly whispering coordinates from other dimensions. What it can do, and what researchers across physics, mathematics, and philosophy have spent decades exploring, is offer a genuinely new lens on the same ancient question, built from the strangest and most well-tested science humanity has ever produced. One of the more serious frameworks for thinking about this comes from Oxford philosopher Nick Bostrom, who in 2003 formalized what's now known as the simulation argument. Bostrom's reasoning wasn't a claim that we're definitely living inside a computer simulation run by some future civilization, but a structured argument that at least one of 3 propositions must be true. Either civilizations at our level of development almost always go extinct before they become advanced enough to run detailed simulations of their own history, or advanced civilizations that could run such simulations choose not to, or we ourselves are almost certainly living inside one right now. Bostrom's own estimate is more measured than the internet tends to portray it. He has stated he personally assigns less than 50% probability to the idea that we're actually in a simulation, but the structure of the argument itself is difficult to dismiss outright, and it has been taken seriously by philosophers, physicists, and technologists for over 2 decades now. Howard dread Philopedia. Physicist Max Tegmark pushed the idea in a different but related direction with what he calls the mathematical universe hypothesis. Tegmark's argument is that physical reality isn't merely described by mathematics, the way a map describes a territory, but that reality actually is a mathematical structure, full stop. Under this view, asking who built the universe becomes almost the wrong kind of question, because it assumes a builder had to exist separately from the thing being built. If reality simply is mathematics, existing the way numbers exist, then the universe wouldn't need to be constructed by an outside agent any more than the number 7 needs a factory. It would simply be one of the structures that necessarily exists, the same way certain mathematical truths are true regardless of whether anyone ever discovers them. This is where quantum computing and cosmic philosophy start to genuinely intersect, because machines like Willow are, in a very real sense, physical devices built specifically to exploit and reveal the deep mathematical structure underlying reality. Every qubit inside Willow operates according to the equations of quantum mechanics, the same equations that describe how electrons occupy energy levels, how photons behave as both particles and waves, and how the entangled correlations Einstein distrusted actually hold up under decades of rigorous experimental testing. When physicists build something like Willow and watch it perform calculations that would be functionally impossible for any classical machine, they aren't just building a faster calculator. They're building a working demonstration that the mathematical rules governing reality at its smallest scales are not just descriptions on a chalkboard. They're operational, exploitable, and in Willow's case, harnessable for computation that outstrips anything the classical world can produce. None of this proves the universe was built by anyone, or reveals a hidden signature left behind by a creator. But it does reframe the question in a way that's arguably more honest than the myths humans have told for millennia. Instead of asking who built the universe as though searching for a name or a face, modern physics increasingly asks what kind of structure the universe has, and whether that structure implies design, necessity, randomness, or something science doesn't yet have the vocabulary to describe. Quantum field theory suggests that even seemingly empty space isn't truly empty, but is filled with fluctuating fields that can spontaneously produce particle pairs, an idea supported by real experimental evidence like the Casimir effect, where two uncharged metal plates placed extremely close together in a vacuum are pushed together by the pressure of quantum fluctuations in the empty space between them. If particles can flicker in and out of existence from what looks like nothing, then the old assumption that something can't come from nothing starts to look less like an ironclad law and more like an intuition built for a world of apples and rocks, not one built for the quantum vacuum. There's also a serious body of theoretical work exploring whether the universe's fundamental constants, the exact strength of gravity, the exact mass of an electron, the exact value of the cosmological constant, are fine-tuned in a way that makes life possible, or whether they simply had to fall somewhere and we happen to exist in a universe where the numbers worked out. This is sometimes called the fine-tuning problem, and it has produced genuinely divided opinions among serious physicists. Some argue the fine-tuning implies a multiverse, an enormous, perhaps infinite, collection of universes with different physical constants, of which ours is simply one where the numbers happened to allow atoms, stars, and eventually observers capable of asking these questions to exist. Others argue that our understanding of what counts as fine-tuned is itself limited, shaped by the fact that we can only observe the one universe we happen to be in, making it statistically impossible to know whether our constants are actually unusual or perfectly ordinary. What a machine like Willow adds to this conversation isn't a mystical answer whispered from beyond the veil. It's a demonstration, sitting in a lab in Santa Barbara, that the strange, probabilistic, branching, entangled rules governing reality at its smallest scale are not philosophical speculation. They are engineerable. In October of 2025, Google's team went further, using Willow to run an algorithm they called quantum echoes, which completed a specific quantum simulation roughly 13,000 times faster than the best classical algorithm running on one of the world's fastest supercomputers. That kind of result isn't abstract theory anymore. It's a machine physically exploiting the underlying fabric of reality to do something no classical system can replicate. Which means every time researchers push quantum computing further, they are, in a very real sense, getting a little closer to directly touching the operating rules of the universe itself, even if those rules don't come wrapped in an answer to who wrote them. Cosmic Ventures. So if you actually could sit a machine like Willow down and pose the oldest question in human history, the honest response wouldn't be a cryptic symbol or a hidden message. It would be closer to this. The universe appears to run on a small set of deeply mathematical, deeply strange rules that permit particles to exist in multiple states, that allow information to be linked across vast distances instantaneously, that make empty space anything but empty, and that so far show no sign of a designer's fingerprint separate from the mathematics itself. Whether those rules were chosen, Whether they're one branch among countless others in a multiverse, or whether they simply are, in the same unshakable way that mathematical truths simply are, remains genuinely unresolved. Neil deGrasse Tyson has pointed out in public conversations that the deeper physicists dig into the fundamental nature of reality, the more it starts to resemble information processing rather than solid matter bumping around in empty space, a description that sits remarkably close to what a quantum processor like Willow is built to do. Maybe that's the real answer hiding underneath the question humanity has been asking since the first person looked up at a star-filled sky. Not a name, not a face, not a builder who can be located and interviewed, but a structure. A set of rules so consistent, so mathematically elegant, and so strange that building a machine capable of operating by those same rules required decades of the most advanced physics and engineering humanity has ever produced. Willow doesn't tell us who built the universe. What it tells us, in the coldest and most literal sense, is that the universe was built, in some fundamental way, out of exactly the kind of quantum mathematics, now humming away inside a chip smaller than a fingernail, kept colder than deep space, sealed inside a lab in California. Whether that counts as an answer or simply a more precise version of the same ancient question is something every generation that comes after this one will have to keep asking, probably with tools even stranger than the ones we have right now.